Are you good?
Yeah, I feel it. And that also means I can let people in as well.
Okay.
Yeah, sorry about that.
Okay. Okay, so I'd like to talk about work in progress with Carolina Araujo, Ana Maria Castravet, Ivan Chaltsov, Kento Fujita, Jesus Martinez Garcia, Kostya Shramov, Hendrik Zeus, and Nivedita Visvanathan. So we have a preprint which is on the Max Planck server, but I don't remember the number. You'll find it on Vanya's website otherwise. And this is, so I want to talk about the Calabi problem for Fano 3 things. So, so the problem I'm interested in is whether there exists, so does there exist, when does there exist? A Kähler-Einstein metric on a compact Kähler manifold. So, so what is a Kähler-Einstein metric? So it's a metric such that the Ricci tensor of omega is a constant multiplied by omega. And in particular, this forces that the anti-canonical class should have a definite sign. So essentially, we're only interested in the cases where Kx is canonically, where the variety is canonically polarized, Calabi or Fano. So in the case of canonically polarized varieties, it's a pretty old result due to Aubin and Yao. So Aubin in 76, the existence, Yao in 78. In the case of Calabi-Yao varieties, it's due to Yao. And in the case of Fano varieties, it's slightly more mysterious. So there's well-known obstructions. So there's a theorem due to Matsushima. Which says that if X is a Kähler-Einstein Fano manifold, then the group of automorphisms of X is reductive. So, so in the case of surfaces, so
it's the left and right. Otherwise,
smoother. Okay, so so in the case of Del Pezzo surfaces, so in dimension 2, smooth, we have a complete description of Del Pezzo surfaces as blowups of P2 in a number of points, or P1 cross P1. And this also allows us to describe the automorphism groups. And it's easy to see that the automorphism groups are reductive, except in the case of the blowup of P2 in one point, where you're essentially looking at an automorphism group, which is automorphisms of P2 preserving that point. And so in this case, we get an automorphism group, which is J square semi-direct product PGL2, so non-reductive. And then, I will not try and do anything that's not on my notes when I'm talking about group theory, because I will. And then the blow up of P2 in 2 points is also non-reductive. And in this case, we get the product of two boron subgroups, semi-direct product mu2. And so these are the two non-reductive cases, and it's a theorem due to Tian that all other del Pezzo surfaces, so smooth, are Kähler-Einstein. So I think that's a result was in 1990. Okay, so today I want to talk about dimension 3, and perhaps I'll introduce now the notions of stability that were introduced to describe the existence of Kähler-Einstein metric. So I'm going to look at Q-Fano varieties. So I'm allowing KLT singularities. And I'll just introduce or give a quick definition of these stability notions via degenerations, and in a minute I'll do it using valuations. Okay, so a test configuration of X is the data of pair XL over A1, where X to A1 is a GM equivariant flat proper map. L is a line bundle GM equivariant high ample bundle, and I want that outside of the central fiber this is isomorphic to the pair X minus RKX for some R times A1 times the punctured line.
How does the GM act on the base?
Just by,
On the A1.
it just acts with a T goes to TA, sends A to TA. Okay, so this is a test configuration of X, and we say that so essentially you have the generations, and here, associated to such a test configuration, we associate this Donaldson-Fataki invariant, which was originally defined analytically I'm not going to give a precise definition, but basically this can be defined algebraically using weights of the GM action or intersection numbers. Okay, so we then say that, so this Donaldson-Futaki invariant is used to define a notion of stability on these things. And we say that X is K semi-stable if this invariant is greater or equal to 0 for all test configuration. It's K stable if it is strictly positive for all. If it is K semi-stable and equality implies that XL equal to 0 if and only XL is a trivial test configuration. And then it is K polystable if it is semi-stable and when it is equal to 0, then the central fiber is isomorphic to the thing we started with. Okay, so these are entirely algebraic notions, and what we know is that X is K stable implies that the automorphism group of X is finite. When the automorphism group of X is finite, so if this holds, then X is K stable if and only if it is K polystable. And maybe I'll say some more things about this later. But this implication K stable implies automorphism is finite is in a paper by Bloom and Shu a couple of years ago. Okay. So in a sense, why am I introducing this? Well, there's this theorem due to Chen-Donaldson-Sun, or it's the Yao-Tian-Donaldson conjecture. Which says that if X is a Fano manifold, then X is Keller-Einstein if and only if X is K polystable. So now we have the equivalence of two really hard properties. But But somehow we've brought the discussion back. This brings the discussion back to a purely algebraic setting. I'd like, before I move on to what I really want to talk about, which is how these notions behave in families, I'd like to just give an alternative characterization of these stability notions, which is probably obvious to Miles, Alessio, and but that I found very surprising. So, and that's somehow, and that's most of the work in that preprint is actually using the criteria of stability that I'm about to give now. So these are the valuative criteria due to Fujita and Lee independently. So this is kind of how birational geometry brings you into these into this field. So let's consider X a Q Fano variety. Then I want to consider divisors over X. So and E a divisor over X. So this means that E is a divisor on some model of X. So we have a proper birational morphism Y2X, and E is a divisor on there. Then we can associate to E the log discrepancy. So the log discrepancy of E is like 1 plus the order along E of the relative ky minus f up a star of kx. So this is the log discrepancy. In order to, well, actually, I don't really need to. But then we have this quantity, which is the expected vanishing, or which people call the expected vanishing. And here my Q Fano is dimension n. So this expected vanishing is 1 over the degree of my Fano multiplied by the integral from 0 to infinity of the volume of f up a star of minus kx minus t dt. So, so this is, of course, not an infinite integral. At some stage, you hit the pseudo-effective threshold, and this becomes 0. So if you like, this is the integral from 0 to tau, where tau is the maximum t, such that f up a star of minus kx minus t is effective. And so having defined those two, we can define the so-called beta invariant, which is just the log discrepancy minus the expected vanishing. And the Fujita-Lee criterion tells us that X is K semi-stable if and only if the beta invariant is greater or equal to 0 for every divisor over X. And X is K polystable if and only if it's strictly positive for every divisor over X. So somehow you replace the definition in terms of all possible degenerations by a definition in terms of some invariants associated to divisor all B divisors or all divisors over your variety. So I'd be lying if I was saying this was easier, but
Is that saying that plurieconomical forms don't vanish too often on it?
yeah. Yeah. So then Fujita introduced this notion of divisorially unstable. So X is divisorially unstable if this criterion fails in the simplest possible way. So X is divisorially unstable if there is a divisor not on a model of X, but living on X. There is a divisor E on X with negative beta invariant. So this is the simplest way in which you make it fail. For Del Pezzo's, you know, in a sense, when you see these descriptions of the unstable, it's pretty clear what you're going to need to take to, so you'll take, for example, the line through P and Q or this sort of things. And if you compute, you do get negative beta invariance. Now, this criterion is is easier to work with in some sense, this valuative criterion, because for Fano varieties in small dimension, we have a fairly good description of their effective cone. And so we're able to compute those things in many cases. So let me, I should have said, so in dimension 3, as I'm sure everyone knows here, there are 105 deformation families of Fanos. Of Fano 3 forms. So this is a classification due to Iskowski and Mori-Mukai. And the question that we were trying to answer in that paper was, for which families is the general member Keller-Einstein, or equivalently K polystable. So as I said, for dimension 3, we've got this classification of Fano 3 forms. In particular, we have a fairly good description of the effective cone in each case. And so it's fairly easy to actually determine which Fano 3 forms are divisorially unstable. And so that's a result of Fujita, who shows that there are 26 families of divisorially unstable Fano threefolds. So he basically takes the Matsuki description of all extremal contraction of all these and computes the beta invariant of every divisor that looks suspicious and finds 26 families of these. Now,
Uniform in the family.
so it's the general member is divisible.
Can you give one typical example?
Yeah, in a second. Yeah. Okay, so
No, that one is going to be okay,
yeah,
I think. And if you have 2 points, it's not fun, I think.
yeah. I'll give you two examples, and I'll actually show you examples where it changes in the family.
But maybe you brought it in a chronic. Maybe that's bad. Anyway,
So for divisorially unstable, very often what you do is you take V5, V22, and you blow up in the right loci. So let me give you an example of so the main theorem of that work that I'm talking about is that if X is a general element in a deformation family, of Fano manifolds, then X is K polystable, except unless X is one of the 26 divisorially unstable. Or X is in family 226. So it's a bit like in your papers, there's always a maverick. So here the maverick is 226. And let me say that in many cases, this was already known. So what was known before was about. So this was known for about 65 families. So typically the cases where it was known, so I'm not gonna even try to attribute any of that, but cases where it was known where products toric Fanos, because in the case of toric, K polystability is equivalent to the barycenter of the associated polytope being 0. And so if you look at Batrev's construction, you've got 5 that are Kähler-Einstein, 13 that are non-Kähler-Einstein. Other cases that were known were covers. So there were quite a few work of like families that are double covers or other covers. So mainly the work of Dervan. Okay, so I'd like to perhaps show what happens in the case of 226, and then talk about families where you have both stable and unstable members in the same family. So the Maverick, family 226. So you've basically got only 2 elements in there, and this Fano happens to be the blow up of V5 in a line. The other extreme array is the blow up of a quadric in a twisted cubic. So I'll come back to the description of lines and so on V5 later. But the idea is that you have 2 types of lines on V5. You have the ones with normal bundle O plus O, and then you have the ones with normal bundle O1 plus O minus 1. And each of these families is going to give you exactly 1 member. So this one is, I call X1, this one is X2. And okay, so if you study the geometry of these things, what you find is that if you're in this first family, so in every case, there's exactly 1 hyperplane section that contains this twisted cubic there. If you're in the first family, it's non-singular. It's a non-singular quadric. If you're in the second family, it is a singular quadric. So, so the other side, so in every case, there is a unique hyperplane H, which contains C3 and is contained in Q. So this is a hyperplane section. And so in this case, H is smooth. In this case, H is singular. And so, because the situation is kind of very symmetric, you can find that in this first case here, where H is smooth, the automorphism, so there's an effective GM action on X, and you can actually build a semi-stable degeneration, which happens to be K polystable. Let me sketch how this is done. So here, if you were to consider this degeneration of your smooth quadric to a singular one, and consider a degeneration such that your twisted cubic doesn't go through the singular point. So C3, let's say, goes to C bar 3, not containing the singular point. Then Then taking, so you've constructed this and you blow up into C3, into the twisted cubic all along. So you've got this degeneration and you blow up essentially this quadric over A1 along you know, your curve C, which is over A1. So if you consider this blow up, what you find is a test configuration of your original Fano. Every fiber not over 0 is going to be isomorphic to X1. And so to get a test configuration, what you find is that the central fiber here, X0, is actually a complexity 1. So it's one of those complexity 1 T varieties. So it has an automorphism group, which is GM square times something, semi-direct product mu2. And so applying criteria on T varieties, complexity 1 T varieties, you can see that this one, X0, is K polystable. And from there, you deduce that X1 was K semi-stable, but strictly K semi-stable because something I have not mentioned about how these notions behave in families is that the K polystable degeneration is unique. So here, X1 by this construction is strictly K semi-stable. So here, this X0 is singular. It's a singular, so it's a Q Fano, and it's a singular K polystable Q Fano. On the other side, so when I started with X2, then you can show that the automorphism here, the automorphisms are semi-direct GA, so it's non-reductive. It being non-reductive implies that X2 is not K polystable. This is a theorem of Alper-Schuh, Halpern-Leistner, and all. So just say Schuh plus friends. But you could ask, is it actually K semi-stable? And in fact, if you were to look at, so you have a singular point. So as I said, you have a singular quadric on the other side. And if you take P minus 1 of that singular point on the left-hand side, you will find a divisor. If you blow up this locus, then you find a divisor. The exceptional divisor has negative beta. So blow up Z, which is P minus 1 here of the singular point. To find call the exceptional divisor. you find that beta x of E is strictly negative. So here we have something which is not even semi-stable. So this is properly K unstable. So there's another story that could be told about all of this, which is about how you find like actual unstable elements. And very often this is about like looking at symmetries or particular, like exploiting the symmetries of your Fano. But I'd like to talk about another story, which is about how these notions behave in families. So I guess so that was question 1. Question 2 is, if you know what happens for the general member, what happens for all members? So can we say which Fano threefolds are Keller-Einstein? And so here, I'll switch to slides in a second, and there are some examples. So I'll talk about several families where you have both polystable, semi-stable, polystable, strictly semi-stable members of the family. So I'll just say that we have a complete answer for 71 out of 105 families. And that we expect that in the remaining ones, we expect in many cases all members to be K polystable. I'll switch to slides, I think. Is there anything in the chat that I've missed?
No. I will alert you if there are questions.
Okay. Okay.
No, that's just general background.
Okay. So, so for 27 of the remaining 34 families, we expect that all members are K-stable, and in particular K polystable. And we have individual conjectures for the remaining 7 cases. Now, I'd like to, so, okay, this was slides for another talk, but it's still the main question. So how does K polystability vary in families? So here is an example of a family where you have different behaviors. So here in family 2.24, so we've got divisors of degree 1, 2 in P2 cross P2. So this is a fancy way of saying we've got like something that has two conic bundles. One is actually a P1 bundle and the other is a real conic bundle. And so one way to actually look at those is to try and get your hands onto the discriminant curve of the real conic bundle. And so if you study this discriminant curve, you find that you can describe all smooth members of this family using this form. And so for it to be smooth, you need mu to be in C and mu cube not to be -1. But when mu cube is -1, you actually just get three values for which you have non-Q factorial Q factorial KLT singularities, and then you've got those two special Fano threefolds, Y1 and Y2. So if you look at the equations here, Y1 and Y2 actually have degenerations to X0. And so if you study the automorphism groups, you get that you have an effective action of C star square for most cases, and then an effective action of C star on Y2, and then finite automorphisms for all the others. So what you get is, so you can show using computing another invariant, which is defined in terms of log discrepancy and effective vanishing, that the general member is K polystable for all mu in C, mu cube not equal to -1. And then you have those two strictly semi-stable guys, which are non-K polystable because they have special degenerations to this X0.
Anne-Sophie, you're speaking too quickly. I can't follow.
Yeah.
You write down one family X mu. That you say that depends on exactly one parameter.
Yeah, and then you have another two, two members.
So that Y1 is what happens when mu is equal to 1.
Not exactly. So here, this description is in terms of the discriminant curve of the second conic bundle.
Mu cubed equals -1. It's 3 different roots.
Yeah, and these correspond to singular degenerations.
But why have you only got Y1 and Y2?
Those are not mu cube equals -1.
You say except for 3 cases.
I said that all smooth members, I'm saying all smooth members are either in the first one parameter family,
Yeah.
or in the second family,
Yeah.
or in the third. The Y1 and Y2 are not special cases of X mu. So basically here, what
I also need to absorb this because I don't think I don't think so this is device of we want to. That's the vector space.
Yeah.
Okay. But then you're saying that if you look at these things modulo isomorphism, that there is one dimension family, and then two. So now there is an action of the group of atoms of P2 times the group of atoms of P2, and so you're saying that after this action, they are just there is a one parameter family of orbits, that's the X mu, and there are two isolated orbits.
Yeah.
We don't know isolated what. Maybe they're not isolated. as such. So you know, then one would expect those two to be sort of when we see this kind of thing when we do GIT.
Yeah.
In several examples.
But the story is very similar to GIT.
And we're presumably these orbits have more, and then you're just showing us indeed that they are on the Y's. Where is Y1, by the way, here? Because you don't tell me what the automorphism of Y1.
Y1 has finite automorphisms.
Which is weird,
Yeah.
I guess.
Yeah. Like in a few minutes, I'll show you the family of V.
Of X mu from mu different from the special value.
It's finite.
That's what otherwise means.
It's finite. It's finite automorphisms almost everywhere. It's like
Zero is the correct one.
yeah.
Okay. But I think Max is saying give us time to swallow this.
Yeah.
So the stuff in where the automorphism group jumps would be somewhat less stable.
Yeah.
That's totally makes sense.
I mean, what you'll see is as well, like in the case of V22.
This automorph out 0x, mu equals 0, 2, minus 1 plus minus 1, 3. Those are not the cube roots of -1.
No.
So those are smooth.
Yeah, I'm saying so for the smooth members, I leave aside mu cube is -1, which corresponds to non-smooth members. So I think the non-smooth ones are q factorial KLT. Now for those mu cube not equal to -1, for the three roots of mu cube equals -1, you still get something which is K polystable, except it's singular. But you know, if you define for Q Fanos, it's completely fine. They're just
and so what if one tries to put together the moduli space of this thing?
exactly. That's exactly the question. Or that's you know, what we're trying to understand now. Okay, so I'll leave you with a singular setting. Okay, so maybe that's a useful thing to say. So what you said about GIT, it's exactly the picture. So here you've got like these Zariski open sets for stable, semi-stable, and polystable, you've got the constructible set. Okay, so that's the Donaldson conjecture, V22, the Mukai Umemura. So here we've got a 6-dimensional family. Prime Fano threefolds of genus 12. So basically here's one description. So you take C7, you take a 7-dimensional vector space, a 3-dimensional vector space, and you look at the net of alternating forms on V. And then X, which is the Grassmannian of isotropic 3 spaces of V. So all the 3 planes in V which are killed by this eta. X is a prime Fano threefold of genus 12. And you have this kind of natural parametrization by this omega. Now, so this is the first description of this family. And you can find that there exists a unique, or you can find, there exists this unique member in this family which has a PGL2 action. So this is the Mukai Umemura threefold. And if you started from your V in, you know, as a representation of an SL2, as an SL2 representation, what you'd build would be, you'd find on the nose this Mukai Umemura. Now there's another unique element which has non-reductive automorphism and which has a degeneration to this Mukayu-Memora threefold. And then you've got a one-dimensional family with an effective GM action. And then you've got like the rest, six-dimensional family worth of the rest outside of this one parameter. And what do we know? Well, we know, so Donaldson shows that the Mukayu-Memora is K-polystable. Sorry, so the Mukayu-Memora threefold is K-polystable because there's this degeneration from XA22 to the Mukayu-Memora. We know that it's strictly semi-stable. So it can't be. Then for the one-dimensional family, which has a member which goes through this Mukayu-Memora threefold again, it's a recent paper by Fujita who shows that they're all K-polystable. So there were some, most of the cases were shown by Cheltsov-Shramov, and Fujita just completed it. And all the other members of this family have finite automorphisms. We have K-polystable examples due to Cheltsov and Shramov. And then there's this family of example due to Tian, which is a family of strictly K-semistable examples. So in this case, he just like builds the, the three-dimensional net of alternate. He builds the net of alternating forms so that you have a family of strictly K-semistable members. Now, here, we've got this kind of moduli description of those prime Fano threefolds, or we can describe deformation. How do you describe the unstable elements? So Donaldson has that conjecture, which originally he formulated just near the point representing the Mukayu-Memora threefold. And he says, okay, so you have on the deformation space here on H1 of T at that point, you have a natural SL2C action. And for every small alpha in this nearby deformation, then X alpha is K polystable if and only if alpha is GIT polystable for the SL2C action. When you actually unpack this, this translates as saying that either, so you're K polystable if and only if either you have an effective GM action or no element in the anti-canonical linear system has worse singularities than of that type. And this conjecture, Donaldson expects to hold everywhere. So not just near the Mukayu-Memora threefold point. Can you say again? No, it's not. Well, I don't know. So by the way, Fujita's recent result is that indeed, like the first bit of the conjecture, I guess, or this partially holds. So there's some hope in that, or there's some hope. I'm not sure there's much hope, but there's another way of looking at this conjecture, which is to say, okay, so Mukai has this other description in terms of GIT, and at least, so he shows that the moduli of Fano threefolds of genus 12 is birational to the moduli of plane quartics. And the correspondence kind of works this way. So basically, you give yourself a plane quartic, you look at the variety of 6 gons of that plane quartic, and you get a, if you take the closure, you get a prime Fano of genus 12. Now, the correspondence kind of works in this way that you know, you've got the prime Fano of genus 12. The plane quartic you're associating to it is the Hilbert scheme of lines on X, and the plane that it lives on is the Hilbert scheme of conics on X. So when X is general, you have an irreducible reduced curve. And so, of course, the crazy idea is, how does the polystability of Fanos of genus 12 relate to the GIT stability of plane quartics on the other side? It's not completely crazy, but I'm not sure how much there is in there. So basically, I should speed up. There's this kind of description that you can really describe the form of the curves, of the quartic curves associated to the Fano threefolds. And you do find that for all it's worth, for the cases we know, it is the same thing, that, you know, the moduli spaces are birational. That's not going to give you a description of every unstable or stable varieties, but that's probably among the most intractables. The other cases, so I said there's 7 other families, and maybe I'll stop there, for which you have both unstable and stable. And basically you've got V22, and then you've got 3 families which have to do with the blow-ups of V5. And here, in the case of V5, you're blowing up in a line, in a conic, in a twisted cubic. So the line I've already talked about, it's the Maverick. But then you have similar stories about the conic and the twisted cubic. And here you have, like, you know, a very nice description of the Hilbert scheme of lines, of conics, of cubics on these guys. And the descriptions of, like, you know, stability or the conjectures really have to do, so that was the example I discussed before. But then you have a 1-parameter family 222, which corresponds to blowups of V5 in a conic. And then, you know, these are on the other side, the blowup of a twisted quartic on P3. And you can, so here in that case, the conjecture is that everyone's stable. In the case of twisted cubic, the conjecture is translated into, so the Hilbert scheme of twisted cubic is represented by a Girard-25. And there you're really finding a conjecture in terms of GIT polystability again. So maybe, yeah, I'll stop there. I'll just say that in very many cases, indeed, we have this description, these conjectures which have to do, which always relate to GIT, and you can hope that this is going to be part of the story, but it's a hard story because of this local structure of moduli, where, you know, somehow you're trying to speak about the green bit here, but the map from the green bit to the left-hand side is a complicated map. So I'll stop here.
I'm stopping the recording. Are there any questions?